So this video is about the Schmidt, possibly pronounced incorrectly, process, which is really important in linear algebra, and it comes up again and again in loads of different cases. So for example, conjugate gradients. In particular, it forms a key part of the QR decomposition, which is kind of a classic approach for finding eigenvalues, which is something that we'll probably look at in the next video. But it forms a part of loads and loads of stuff, so it's really important. And what we do is we consider the case where we start off with so a bullet point with a set of linearly independent vectors. That's going to be a v1, let's say, to vn. We've discussed linear independence already in our previous two videos about the power method. So while these v's are linearly independent, they're not necessarily orthogonal. And what we want to do, again, orthogonality discussed in the previous videos on the power method, is we want to create an orthogonal set of vectors, which we're going to write as a q1, let's say to a q n. And what we say is we want those orthogonal vectors to have the same span as our linearly independent vectors. So we're introducing this term span, which has a specific meaning in linear algebra. So to work out what span means, if we look at these vectors defined by the v's, it's essentially all the linear combinations that you can create from these vectors. So the span of the set of vectors, so v1 to vn, is all linear combinations of these vectors. So let's just say, for example, it's equal to the summation from I equals 1 to n of some constant, which I'm going to write as an alpha, multiplied by the vector vi. So it's everything you can create by changing these constants. So it's every vector that you could create through a linear combination of the v's. And then if we write, let's say, the span of q1 to qn, then we're going to say that's the summation. I'm going to have a different constant here, so let's use betas as a constant instead of these q's. And when we use the Gram-Schmidt process, we want to find an orthogonal set of vectors q that span the same space as v. So practically speaking, that means that any vector you can make out of a linear combination of these v's, then you'll be able to recreate that vector using a linear combination of q's, just multiplied by potentially different constants. So you'd be able to find betas that could then recreate any vector that could be made by a linear combination of the v's. And so it's kind of an orthogonalization process, if you like. So the whole thing is about saying, well, we've got these vectors already, they're linearly independent. We want to create a new orthogonal set that has the same span. So we have our vectors v1 to vn that are linearly independent, but they're not orthogonal. And what we want to do is create the vectors q1 to qn, which are orthogonal and span the same space as our v vectors. We're going to start off just by simply picking q1 is equal to v1, so that's our first vector sorted. You have to start somewhere. And we're going to pick q2 by saying we want that q2 is equal to vector v2 plus some constant times Q1. And then what we want to do is choose the constant alpha so that Q2 is orthogonal to Q1. So to do that, we're going to pre-multiply by Q1 transposed. So is equal to Q1 transposed V2 plus alpha Q1 transposed Q1. Now by definition we want Q1 and Q2 to be orthogonal, so this is equal to 0. Therefore what we have is that alpha Q1 transposed Q1 plus Q1 transposed V2 is equal to 0. And so that tells us that if we want Q1 to be orthogonal, if we want Q2 to be orthogonal to Q1, that is, we want to choose Q2 so that it's orthogonal to Q1, then we should set alpha equal to minus Q1 transposed V2 divided by Q1 transposed Q1. So just rearranging this. So substituting alpha back into here, what we're saying is that you should set Q2 is equal to V2 minus this alpha that we've solved for, multiplied by Q1. And you can do this because you have your V2 already, and we also have our Q1 already. Okay, so that's fine. Now we're going to move on to pick Q3. What we're going to say is we want Q3 to be equal to the vector V3 plus, I'm going to have another constant, let's call it a beta, times Q1 plus a gamma times Q2. Very similar procedure now, but basically we're going to choose these constants beta and gamma so that Q3 is orthogonal to Q1 and now Q2. So very similar thing, we're going to pre-multiply by Q1 transposed. So that's equal to Q1 transposed V3 plus beta, the constant we're yet to find, Q1 transposed Q1 plus gamma, another constant we want to find, Q1 transposed Q2. Okay, so by definition, Q1 transposed Q2 is equal to 0 because we did that in the previous step. We deliberately chose a Q2 that's orthogonal to Q1, and also we want it to be the case. We want to choose these constants so that Q1 transposed Q3 is 0. We want those to be orthogonal too. And so after all of that, what we find is that, so I'll write it out in full, Q1 transposed V3 plus beta Q1 transposed Q1 is equal to 0. Therefore, beta will be equal to, so just rearranging this, minus Q1 transposed V3 divided by Q1 transposed Q1. So that's beta sorted. Now to get gamma, we're going to pre-multiply by Q2. So very similar now, very similar process. I'm sure you can see where this is going, but Q2 transposed Q3 is equal to Q2 transposed V3 plus our beta, which we have found now, but we'll just see this through. So Q2 transposed Q1 plus gamma that we're yet to find, Q2 transposed Q2. Okay, so we found beta, but it doesn't really matter because we've already chosen, as we say, Q2 to be orthogonal to Q1. So this is going to disappear. Likewise, we want to enforce that Q2 and Q3 are orthogonal, so that's going to disappear as well. And so rearranging this in exactly the same way as just previously, then we can see that gamma will be equal to a minus Q2 transposed V3 divided by Q2 transposed Q2. Okay. So we put all of that together, and what you end up with is that this third vector, Q3, is equal to a V3 minus, so this was our beta. It's going to be a Q1 transposed V3 divided by Q1 transposed Q1 multiplied by Q1, then minus again. So this is going to be our gamma, so it's just up here, Q2 transposed V3 divided by Q2 transposed Q2 multiplied by vector Q2. So you can see as we proceed iteratively, we can keep finding these new Q's. So for example, in this case, what do we need to find Q3? Well, we need V3, which we had already, and the only other things that we need are the Q1s and Q2s. And we found those in basically the previous iterations of the algorithm. And if you keep going, you can see the pattern. It's relatively easy to see that in general, if you want to find vector Qj, so we've already found Q1 to Qj minus 1 by this point in previous iterations of the algorithm, then this is equal to Vj minus summation from, so here I'm going to use an I equals 1, j minus 1, and basically we've got these constants here. So we're going to have a Qi transposed, because you can see this increases. This is like I'm just wrapping all this into a single summation, multiplied by Vj, so you can see that V3 is consistent, it's always V3 in these terms, and then divided by Qi transposed Qi, again multiplied by Qi on the end. And that completes the algorithm, essentially. So now we're going to try and think about what's happening geometrically by defining something called the projection operator. So let's imagine we have a vector x and a vector y. Then if you draw, let's say, some dashed lines here, this is a right angle, then this vector here, which we're going to call P, is the projection of y onto x. In other words, it's the component of y that's acting in the x direction. By definition, P points in the same direction as x, so this is equal to a constant that we don't know multiplied by x. Now through vector addition, we know that if you, let's say, travel along the vector y and then travel along the vector minus p, then you'll end up here. So you end up actually orthogonal to x. So that vector there is equal to y minus p. As we said, this vector is orthogonal to x, and so by definition that means we can write that x transposed multiplied by y minus p is equal to 0. And so x transposed y minus x transposed p is equal to 0. We then substitute in that p is equal to a constant times x, because p points in the same direction as the vector x. So we find that x transposed y minus constant x transposed x is equal to 0. Therefore, after rearranging this, you find that the constant is equal to x transposed y divided by x transpose x. So putting these things together, we end up with the projection is equal to the constant, which we've just found, just geometrically multiplied by the vector x. And we introduce a bit of notation here to make this a bit simpler to write down. We take all of this stuff, and instead of writing it down each time and remembering what this represents geometrically, we write this down as the projection onto x of y. So now we've got this definition of the projection operator, we'll plug it back into our Schmidt algorithm to see what geometrical interpretation that gives us. So going back to our algorithm, we now know that we can write Qj is equal to Vj minus the same summation over I equals 1 to j minus 1. And then here we're going to write the projection onto Qi of Vj. So we're going to look at what this means, starting in 2 dimensions. So let's say we have our vector v1 and a vector v2, which I've drawn deliberately so that they are linearly independent, but they are not orthogonal. And remember that we start off by setting q1 equal to v1. Then the second iteration of our algorithm, when we're trying to find q2, what we do is we set q2 is equal to v2 minus the projection onto q1 of v2. Okay, so the projection onto v1 of q2 is the component projection onto q1 of v2. We draw another dashed line here, is equal to that vector there. Okay, that's the component of v2 which is acting along v1. And we're saying that q2 is v2 minus this projection. So you can see that if you go travel along this vector and then travel in the negative along the negative component of the projection of v2 onto q1, then we end up here. So you've gone along here and then along here to arrive at this vector, which we call q2. And so geometrically you can see that q2 is going to be orthogonal to q1. So now I'm going to try and give another example for the next iteration. So when you're trying to find q3, although it's not very easy to draw, but we'll give it a go. So iteration 3. So let's say you've already found your q1 and your q2. Now you want to find q3. Then we know that this is going to be set as equal to v3 minus the projection onto q1 of v3, and then minus the projection onto q2 of v3. So down here I'm going to draw, again attempting some 3D. Let's say that this is q1 and this is q2, which is by definition orthogonal to q1. And then I'm going to draw this vector v3, which, okay, so through these dashed lines I'm going to try and indicate where it lies. So if we draw this dashed line down to here, then that's where it lies on the Q1 kind of axis. And this dashed line here shows where it lies on the Q2 axis. Okay, so we're going to look at these two terms. So first of all, we're going to consider the projection onto Q1 of V3. So the component of V3 that lies along this axis is this vector here that I'm going to draw in red. So that is projection onto Q1 of V3. Then we look at our second term. We say, okay, well that's a projection onto Q2 of V3. So the component of V3 that lies along this axis. So I'm going to draw that here. So that is projection onto Q2 of V3. And then let's perhaps choose a different colour for this next bit. So our Q3 is, what we're going to do is, again, just kind of follow geometrically this vector addition that we see here. So it's V3, so we travel along V3, minus the projection onto Q1 of V3. So that's this vector here. So we travel along here, and then we go backwards, basically, along Q1. We end up at a point above here on the Q2 axis. So we travel along here and then along there, and then minus the projection onto Q2 of V3, which is this vector here. So then we travel backwards along the Q2 axis to get to here. And so then what we end up with is Q3 being this vector, which, as you can see, geometrically is orthogonal to Q1 and Q2. So that gives an idea of how these, using the projection operator and drawing some pictures, it gives you an idea of the geometry of everything that's happening. So before we finish this video, it's worth noting some of the language around this because it can be a bit confusing. So this kind of operation, you might see it written as, for example, that Q3 is orthogonalized with respect to Q1 in Q2. So that's the first bit of language that you might see written. Or, for example, given the geometry of the thing we're looking at, you might say that Q3 is orthogonalized by taking V3 and removing its projections onto Q1 and Q2. So that's referring to the fact that we're taking off these kind of projection operators. Right, the final thing we need to do is make sure that the span of our new orthogonal vectors is equal to the span of the original linearly independent vectors. So remember that, we'll kind of sketch a proof out here. Remember that Q1 is equal to V1, and so those vectors are pointing in the same direction. So by definition, the span of Q1 is going to be equal to the span of V1. Okay, so far so good. And then we remember that Q2 is equal to V2 minus the projection onto Q1 of V2. Okay, well, Q1 is equal to V1. So what we've got is Q2 is made out of V2 and some sort of projection onto V1. So in other words, it's made out of a linear combination of the vectors V1 and V2. So from that, we know that the span of Q2 is equal to the span of V1 and V2. Like I say, because Q2 is made of a linear combination of V2 and some sort of projection onto V1. We keep going, so we'll do one more. Let's say that Q3 is equal to, so remember it's going to be V3 minus the projection onto Q1 of V3 minus the projection onto Q2 of V3. Okay, so obviously there's a component of V3 in Q3. We have a projection again onto Q1, which is equal to V1. So we have a component acting in the V1 direction, if you like. Then we also have a projection onto Q2. But we already know that Q2 can be expressed as a linear combination of V1 and V2. So if that's linear combination of V1 and V2, this is in the V1 direction, and this is a component in the V3 direction. So putting all that together means that the span of Q3 is going to be equal to the span of V1, V2, and V3. And we can continue with that logic to arbitrary Q. So putting all that together, that means that, well, for this case, if Q3 is spanned by V1, V2, and V3, Q2 is spanned by V1 and V2, and Q1 is spanned by V1 only. If we put them all together, basically each one of these Q's can be expressed, so I'll go all the way to Qn, as a linear combination of V's. And so that means that the space that's spanned by the Q's is equal to the space that's spanned by the V's. Okay, and so that concludes everything. We've used the Gram-Schmidt method to create this orthogonal basis, which has the same span as our original linearly independent vectors. Next video, I think we'll look at the QR algorithm, which is an interesting application of the Gram-Schmidt process.